Hi, my name is Ali Zahrai, and this presentation is for Physical Cyber System during fall 2019 semester. The selected paper called Characterizing Cyber Physical Attack on Water Distribution System. Interestingly, this paper has five authors, and each author has relatively different background. They are a bunch of group of engineer and computer scientists, and they are trying to tackle a real world problem. This paper published back in 2017 for American Society of Civil Engineers Journal of Water Resources Planning and Management. Interestingly, it has a combination of engineering and computer science at the same time in an almost real case. Paper start with some background information. Paper suggests that breakthrough represented by cyber-physical system and Internet of Things and Internet of Service induce experts to collectively term these new paradigm as the fourth industrial revolution. In case of a smart water network, CPS build on the interaction between physical water assets and network devices designed to monitor, operate, and supervise systems. A smart water network includes five main components: combination of sensors, mobile sensors, smart meters, programmable logic controller, or as what we call them PLCs, and supervisory control and data acquisition. A SCADA system is the case in this paper, which is basically a centralized computer employed to supervise the operation of the entire infrastructure. Each modern water distribution system has some certain features. Usually modern water distribution systems superior in reliability, autonomy, and efficiency, and expose both physical and cyber infrastructure to cyber physical attack. However, these attacks, such as accessing of private consumer or operational information to intentional damage to the physical water assets, for example, pumps, valves, tanks, and etc., decreases of water supply and even impact on water quality. Safety critical role played by water distribution system make those advanced modern systems attractive targets for terrorism and cyber warfare. Several cyber-physical attacks have already occurred against United States water utility in the past couple of years. And more importantly, vulnerability of water network, lack of analytical and computational tools that merge models of physical processes, control, and communication systems. The paper objective is mainly twofold. This paper introduced a combination of an advanced attack adversary model and a MATLAB toolbox that called EPANet, which basically take responsibility of simulation. Basically, this paper tried to simulate an advanced and a smart water distribution system in a fairly large city and try at the same time to come up with a combination of advanced attack model, and those attack models are simulated using EPANet CPA, which is a newer version of EPANet for distribution system modeling. The proposed framework can be seamlessly extended to model attack aimed at disrupting the infrastructure and affecting water. The attack model proposed by this paper has two main goals. The first goal is that the element of the cyber and physical space that can be attacked should be identified, and when those items are identified, the type of attack might be subjected to is also should be decided. Graphical representation of the attack for a simple distribution network consisting of one pump, one valve, one tank, and a few demand nodes is presented on the right. The attack model lists 9 different types of attack. Classification of those attacks are mainly on the basis of the type of element being attacked that targets sensors, actuators, PLCs, and sometimes SCADA or our centralized system, or the communication links of those elements. By total, there are 9 different kinds of attack tested by this research paper, and the first 2 attacks are basically focused on the physical layer of a distribution system. Attack number 3 and 4 are mainly focused on the physical link of 2 components. For example, here the physical link between a PLC and a valve. Attack scenario of 5 to 7 mainly focus on link between PLC to PLC or a PLC to SCADA. Those red attacks here are basically focused on, for example, here a PLC and SCADA system. And attack 8 to 9 basically is a direct attack on PLC and SCADA itself. There are a bunch of, as it previously mentioned, attack model or adversary model, and they are separated based on that certain element that has been attacked. Attack number 1 is basically a physical attack to a sensor. How that attack happens is that usually attacker is supposed to have direct physical access to a sensor, such as the water level sensor. And there are going to be a bunch of consequences. The main consequences is that typically PLC connected to that sensors may receive null or altered reading that eventually compromise controlling operations. Attack number 2 is also a physical attack, similar to attack number 1, but this time to an actuator. And how it typically happens is by a similar attack to attack number 1 is based on the physical access to a system component actuator. And the consequence of this attack number 2 could be various, but can cause DOS or compromise the operational integrity of system, and unlikely and not be perceived as cyber. Attacks 3 and 4 are a little bit different based on that component that has been attacked. Here, the attack is mainly usually focused on those connection link. For example, attack number 3 is attack to the connection link between a sensor and a PLC. How it happens is the type of connection link between two determine whether the attacker needs physical access to the sensor to perpetrate its actions, and the consequences might be different. These actions include denial of service, manipulation of data package being sent to the PLC, and eavesdropping. Similarly, attack number 4 is the connection link, but this time between the PLC and controller actuator. How these sort of attack happen is adversary physically or remotely interrupt the connection between PLC and control components such as the valve, and it consequently might have valve fail to acknowledge new control signal. Attack 5, 6, and 7 are slightly different. They are basically the connection link between two PLC, for example, attack number 5. PLC generally connected through a private network or internet to exchange information on the system state. PLC gather data from, for example, tank water level sensors and transmit them to PLC2, which control the pump on the basis of tank water level. And as a result, a disruption of normal pumping operation and different PLC might have different readings from the same sensor. These are few consequences that could be expected. On the other hand, attack number C is slightly different. It's attack to the connecting link between a PLC and a SCADA. And it typically happens by the PLC to SCADA communication being attacked or manipulated, eavesdropped, or temporarily interrupted. And consequently, it might cause incomplete or wrong key information on the system state that eventually reach to a SCADA, and the adversary might resort to this attack to conceal other action from human operators. Attack 7 or 8 are also a different category depending on what element has been attacked. Attack number 7 is attack on the connecting link between SCADA and PLC, and it usually happens by the signal sent by the SCADA to a PLC are blocked and either manipulated or eavesdropped by the adversary, and consequently disruption of normal pumping operation, and different PLCs might have different reading from the same sensors. Attack number 8 or 9 are again kind of different. They are a direct attack on a component. Attack number 8 is attack on the PLC itself. Typically, adversary has direct control of a PLC in a network, and consequently, depending on the level of control gained by the adversary, the attacker may completely stop normal operation of the control process, manipulate the control logic in the PLC, or deliberately report incorrect data to the SCADA that could eventually lead to the whole system to be compromised. Attack number 9 is similar, that actually an element, a control element, is directly attacked, but this time on the SCADA, and usually attacker has compromised the SCADA system either through a local or remote attack. Consequently, a compromised control system such as SCADA system cannot be detected because the detection happened in SCADA later and is able to arbitrarily change any system configuration and obtain all data measured by sensors. These are so far 9 separated attacks, but what happened in reality is usually a little different. In reality, usually adversary may perform multiple attacks in sequence or target several components at the same time. Also, attacker might first eavesdrop a communication channel to later perform a more sophisticated attack. Therefore, in reality, what happened is a combination of these attacks either at the same time or in a sequence that makes them much harder to understand, identify, or resolve the problem. The case study here that has been used for the simulation part is relatively a mid-size water distribution system for a city called C-Town. The physical characteristics of C-Town water distribution system are on the top. This system has about 400 nodes, about 400 pipe, 7 tanks, and 11 pumps, and eventually there are 4 major valves associated to this system. Main characteristic of C-Town PLCs is that PLCs, each of these 9 PLC is connected to sensors and actuators. For example, PLC number 3 is connected to sensor T2 that basically controls tank 2, water level at tank 2, and also is connected to a bunch of actuators. For example, valve 1 or pump 4 or pump 5. This is a schematic representation of C-Town water distribution system. And this is exactly what has been modeled through CPA, EPANet CPA, that basically take care of simulation part of those previously defined attacks. There are a bunch of simulation steps here. The first one is that water storage and distribution across the demand node is granted by 7 tanks. Tank water level trigger the operation of 11 pumps. Pumps, valves, and tank water level sensor are connected to 9 PLC. Hydraulic simulation is carried out with EPANet with a simulation horizon and hydraulic time step of almost 7 days and every step of about 1 hour. EPANet CPA is an extension and relatively new added feature of EPANet to the realm of cyber physical security. EPANet, for those of you who are not familiar, is basically an engineered toolbox that provide the simulation of a large-scale water distribution system. And EPANet CPA is basically this EPANet but with more capability to model attack on water distribution system. The component of a simulation-based risk assessment model for water distribution system are schematically presented here. Interplay between components for simulation-based risk assessment of cyber-physical attacks on water distribution system has many components. For example, for this specific research, those components in gray are those ones that they are somehow investigated through this project. And those elements that they are white, they are basically left out from this research. So this also shows the level of complexity of a real attack. Those white elements are not yet considered, but any of those ones can be an attacking point to the water distribution system. In order to quantify the impact and severity of any of these attacks on the smart water distribution system of Seatown, there are three defined parameters that shows what is the significance of that particular attack. For example, total tank overflow or VTOT is defined as a total amount of water spilling over an attack tank. So basically, the more the VTOT, the severe the attack. That's the amount of water that is spilled. The second one is the total time at low level or T-low, which is defined as the total amount of time during which an attack tank is in low level. So again, the greater this value, the more actually significant the attack. And the third one is the relative variation in pump's power consumption. It's basically a percentage and is the ratio to normal condition. The higher this value shows, the more actually pump has worked, which shows there is something wrong with the system, that pump has been overused during a specific time frame. There are a bunch of attack scenarios that each attack scenario uses a combination of those previously defined attack model and some certain level of that water distribution system. Attack scenario number one is called attack overflow due to a direct attack to a booster station. Normal operation pump PU1 is generally active while pumping PU2 is switched on only when a surge in demand causes tank T1 to empty faster. For this scenario, attacker takes control of both pumps at time T and forces both pumps to run. This flowchart shows, this graph shows tank 1 water level and versus the simulation time. Obviously, after time 10, it shows that there is starting to have some divergence between the normal condition of normal situation versus the real versus attack situation. After time 10 or 10 hour, we see that there is a divergence. Also, interestingly, this paper presents the value measured of water level 1 at PLC2 and SCADA. And as you can see here, since there is no certain attack on a PLC to SCADA, so basically there is no significant difference between the value shown on a PLC2 versus SCADA. On the other hand, attack scenario number 2 is called low level in a tank due to a manipulated water level readings. Water level readings in tank 2 are altered to prevent the tank from refilling. When T2 water level reading collected by PLC3 are temporarily altered to a value triggering valve of V1 closure, the tank is disconnected from the main line and eventually result in a quick decrease of water level. Again here, as we can see, this is tank 2 water level and this is tank 4 water level versus time. And this gray line is a normal condition and the darker black line is the true attack. And we have two of the circle and square. Each one shows either PLC or SCADA presentation of that water level. As you can see, first there is a divergence at some point here at time 50, which is exactly when the attack started. And along the process of these attacks, there is no major difference between the value shown by PLC and SCADA, which shows these two elements are left out from these attack scenario. However, we can tell that we have too much of water comparing to normal condition, or minimum water comparing to the normal condition. So significantly tank 2 is compromised. Tank 4, on the other hand, is less compromised, and except some certain time in the middle, there is no significant difference from the no attack scenario and the attack scenario. Scenario number 3 is attack workflow due to an alteration of PLC to PLC connection. Attacker modified the information on tank T1 and water level sent by PLC2 to PLC1, which control pump 1 and pump 2. The water level time series here associated to PLC2 and PLC1 differs. So obviously you can see that this is the simulation versus tank 1 level. This gray is the normal scenario, and the true scenario or attack scenario or dark black scenario. And PLC2 and PLC1 are presented, and you can tell that at some point after time around 100, there is significant difference between what has been shown from these two scenarios, two PLCs and SCADA. And value of tank T1 water level received by PLC1 triggered the activation of pump 1 and pump 2, which eventually lead to a sharp increase of water level at tank 1, which is right here. Another scenario is more complex scenario. Scenario number 4 is a concealment via reply attack on PLC to a SCADA connection. This is a more advanced and completed version of previous scenario by attacking the communication now link between PLC2 and SCADA. Here, adversary first eavesdrop the PLC2 to SCADA connection and then decipher the signal and store tank 1 readings from the first 48 hours of simulation. Also, SCADA received plausible information on tank 1 water level that is rising sharply. This is again tank 1 water level versus time, simulation time, no attack scenario, true attack scenario, PLC2, PLC1 observation, and SCADA. And we can tell that there are significant attacks starting at this point, and there are two different observations observed by PLCs and SCADA, and there is a significant difference between behavior of the water level after the scenario actually is started. Scenario number 5, called tank overflow due to wrong settings sent by SCADA. Attacker to the SCADA to PLC connection this time modify the threshold for the activation and deactivation of pump 11 for approximately 50 hours. That causes pump 11 to be active during the entire period. So obviously from attack scenario number 5, we expect that third indicator to be pretty high for the efficiency of the pumps. And these scenarios result in an increase of tank 7 water level, which trigger PLC9 to deactivate pump 10. This is again for tank water level of 7, pump performance and pump performance of 10, and pump performance of 1 versus time. And as we can see, there is significant difference between a normal condition and actually the attack condition. Specifically, pumps actually act completely differently. That may cause actually to have a lot of energy consumption versus normal condition. Attack number 6 is basically a random multiple attack on various PLCs. And there are a bunch of random attack and responses of C-town network. Under 100 randomized attack has been illustrated here. And each simulation features a sequence of 3 attacks basically aimed at driving each tank to overflow. Sequence comprise the manipulative attack on attack T2 water level reading being sent to PLC 3, and 2 attacks on PLC 6 to 3 and PLC 4 to 3 and other communication link. And high relay response of the network is largely influenced by the starting time. Depending on where that random attack is started, the network behaves completely differently based on the water level and the current status of the system. Here, this table shows a summary of those scenarios. Basically, for example, it shows that scenario number 4, attack number 4 basically used that attack 5 and 6 scenario both at the same time. The target are basically PLC 2 to PLC 1, and action has been taken through that. Attack number 5 is a combination of scenario 5 and 6 is to alter T1 level to PLC 1, and the effect is pump 1 and pump 2 are on, and they happen usually after 50 hours, and T1 basically overflow up to more than 10 cubic meters. So this is the summary of the results of that 6 scenario attack. And each attack, for example, attack number 4, use a combination of previously presented attack, for example, attack 4 and 6. And this is representative of that 3 indicator that shows what has been the consequence of any of that 5 scenario attack. For example, as we just mentioned, on scenario number 4 and 5, the pumps actually overreact to the system, and we have a lot of energy consumption. For scenario number 1, we have a lot of total water actually, so we have a lot of overflow of the water versus the normal condition. Or for scenario number 2 and 3, we have a lot of actually less water comparing to the normal condition that we should have. So these indicators basically present how much extra water we had, how many hours we had below the normal surface elevation of each tank, and how much extra energy consumption we had. So an attack might actually have various kind of consequences depending on any of these attacks and what element has been attacked through that specific scenario. So in conclusion, that would be the last slide, is same hydraulic response obtained through different attacks. So that makes it significantly different for an operator to understand where that attack comes from. Attack might start from a PLC, a link, and SCADA, a valve, an actuator, but they all might end up to the same consequence, which make it significantly different. Eavesdropping attack are potentially very dangerous because the adversary can use information on the system behavior to design sophisticated attacks that not only undermine the system, but also the integrity of data. Also, results show that the hydraulic response of a water distribution network to cyber-physical attack is largely influenced by the system initial condition and what is the current status of system that attack actually happened. Thank you so much for your time.